Good afternoon, everyone. I hope you can hear me. And welcome to today's research seminar. It is my pleasure to introduce Kristin Kerem, an early stage researcher at TalTech Estonian Maritime Academy, who will be presenting on a fascinating and forward-thinking topic. Can you hear me?
Yes, we do.
Yes? Okay. The topic is Wing and Ground Craft Airship, a new sustainable vessel using ground effect to fly the seas. Kristin's work reflects our ongoing commitment to innovation and sustainability in the maritime field, and I encourage you all to engage and ask questions after the presentation and contribute to the discussion. I'd also like to mention that today's seminar is being recorded and will be uploaded to the Maritime YouTube channel, so you can revisit the discussion or share it with colleagues who couldn't attend. So I think we can begin. Kristin, the floor is yours.
Thank you, Kirsti, for inviting me to talk about the topic that I've been researching for 2 years now and continue for another 2. Wing and ground vessels and how to use them. Before we begin, I ask kindly everybody, if you have a question, just write it to chat. And whenever I have the possibility, I will start answering them. I hope this way it will be more interactive and we get more out of the seminar than we would on the other way. As Kirsti said, my background is in maritime transport. I'm the graduate from TalTech Estonian, finishing my master thesis last year and now continuing in maritime transport research group. And my main interest is legal research of maritime, but especially in terms of new technologies. So what am I going to talk about today? I have 3 objectives that to tell you about. First, what is such a ground effect vessel and why it's very actual today. What is the project AIRSHIP that we're working on, and what is the part that TalTech and our team is doing in it. Before we start, we need to understand what is ground effect. And the easiest way to understand this is to see how the birds fly. As you can see, they fly low to the ground, minimal effect, they don't move their wings at all. So they do it almost like effortlessly. And when you look a bit on this video further, you will see that as soon as they need to get out of this zone where they are very close to the water, they need to do some effort to keep their movement going. You will see them soon flying back. They're moving their wings when they are not so close to the water. And now they go close to the water in the remaining gliding zone. And that is what this project is after. We want to use the ground effect to move forward and fast. And this project has been called as flying ships above the oceans and inland waterways. Then the initial idea of having a flying ship is actually rather old. It's one drawing from 16th century made by Leonardo da Vinci, rather famous one where everybody ridiculed him at the time. How can ships fly? Today we know them as airplanes, and in a way, ground effect ships are similar to what he had back in mind then. Now fast forward a few hundred years, and we arrived to 1904. The Wright brothers in the United States and their second attempt to have a flying vessel called Flyer 2. There's 2 modifications of it. And they did the first test flights with that one and understood that it can stay in the air close to the ground longer than it can stay in the air without the engine. So they, in a way, discovered the ground effect as it can be used with airplanes. Now, fast forward another few tens of years, and we arrived to 1967, 5 years after the Cuban crisis. And CIA gets a report from Caspian Sea that there's a new monster there, something big, reminds your ship because it's floating, but it looks like an airplane. And Russians called that technique aeroplan, ekranoplan. And the reason was that it was combining two ways of moving, first in the air and then on top of the sea. Kind of amphibian, but not coming to the ground. And Russians are still known as the ones who have taken this technology the furthest. In the end of the 1980s, the picture that you have now on the left is one of the top designs called Lun, which was meant to be moving close to the waters. As you can see, it's a barely few meters above the water, being therefore stealth and unrecognizable for the others. Sadly, or not so sadly, when we look at it from our perspective today, their development was stopped by the end of Soviet Union, and ground effect ships development also stopped for quite many years. Now, what is ground effect as such? It got its name in the 1930s after analysis had been made about the flights in the Second World War, where pilots found out that they have an interesting feature. When their aircraft is hit, but they manage to come close to the water, they can stay above the water long enough to reduce the speed so that they can make a safe landing. And in 1935, it was presented to the Congress in a report that is rather well known and is one of the basis of documents on ground effect, compiled by Mr. Maurice Lesueur, originally from France, but for some reason France has never been very well known in this field of study. So what is ground effect? Basically, it happens above any surface. We today are talking in maritime domain, which means that we are talking about using it on top of the sea. And the idea is that when you have a moving object that has some sort of speed, it moves through the air and creates two types of pressures. It compresses the air which is underneath, creating overpressure, and it has a bit lower pressure on top of the wings. So when the subject then in the flying mode comes close to the ground, so much that the pressure under the wings is carrying it in a way, then this aircraft does not need additional speed to stay flying. It is also in a danger zone because you see that there is outward airflow that happens from pressure air released from the wings, which can create the effect that the air escapes, turns the ship around and so on. So when you look at the aviation rules and regulations, then you will see that flying in the moments of takeoff and landing are the most dangerous things. And ground effect happens basically in those moments. And all airline pilots will tell you that they will avoid flying low whenever they can. However, this whole technology is based on flying as low as possible, close to the object, taking maximum advantage of this additional pressure that is created under the vessel. Now, we can talk that this technology is something new and something from Cosmos and not very widely used, when actually it has been around for centuries and it has been used for quite long. For example, in the left photo, you have trains that are being developed in Japan to have extra speed with minimal use of fuel. It's quite well used on Formula Ones and any race cars, where it's used in opposite direction. The car is as low as possible to the ground from the front so that the low air pressure would be under the car and higher on top, keeping the car close to the ground and therefore enabling it to move faster. On the right-hand side, lower picture, you have a hovercraft, well-known vehicle which uses the same air pressure like we saw in the previous slide, Only difference from ground effect vehicles being that these ends of wings have usually around them additional layer of rubber that keeps this pressurized air underneath, and that enables them to move also on top of the ground. The left side is combination of ground effect vehicle and a drone. Very often people want to say that ground effect vehicles and drones are one and the same thing, but they are not. The drone usually has blades that you can see and they move in a horizontal direction. When we talk about wind and ground vehicles, then they usually have blades that, if they have blades and not turbo engines, these are on top of the aircraft, similar to the hovercraft and in similar position. So ground effect is something that happens naturally in birds. We can take and use it to fly low to the ground. And from this, 2 years ago, an AIRSHIP project was started. It has 7 different members in universities, and it's led by Politécnica de Madrid, Polytechnical University of Madrid, by 2 of their groups, robotics and industrial electronics. We have partners from La Palma Research Center in Spain, Canary Islands, Tech from Portugal, and Risolar is also from Portugal. TalTech, Tampere University from Finland, and University of Luxembourg from Luxembourg. So the project will last for 4 years, and the budget is quite significant. It's 5.1 million, of which 10% is part of TalTech's. And why is this research being done? When you look on the sketch on the right-hand side, where it's comparing speed of different kind of vehicles to the amount of power they need to move forward, then you will see that the wing and ground vehicles fall into the categories of red, which means that they use a bit more power to move forward than traditional ships, which means that they are also faster. They are a bit slower than the aircraft, but they use way less energy than the aircraft. So the efficiency comes from speed. Average speed that can be reached by this vehicle is about 200 kilometers per hour. However, the bigger the vehicle, the more faster it will become. When you compare it for hydrofoil ferries, for example, then the speed is 75 kilometers per hour. So it's way faster than anything else we have on the waters today. The efficiency comes from using this ground effect as a way to carry its weight forward, which means that it can carry half more of payload, half more of goods on its back than a traditional airplane of same size, and still using about up to 80% less of fuel. So that's why this theme is rather interesting, especially when we are talking about maritime decarbonization and finding ways how we can reduce our carbon impact. And of course, having faster transports and way to transport goods is always interesting. And in the AIRSHIP project, we are aiming to make it even better by making it fully electric, which means that it will have a loading docks on both sides or one side where it starts or finishes its journey, and it will have next to 0 emissions during the travel. Now, the next question people usually ask is that why are we talking about in maritime domain? Why we are not talking about it in avionics? Why not about airplanes? And the reason is an agreement which was done in the 1990s between IMO, International Maritime Organization, and ICAO, International Civil Air Avionics Organization, which has agreed that all wing and ground crafts, that's now a specific term for IMO and maritime use of such vessels, if they fly lower than 150 meters of height and they do it above water, they are considered ships. Reason being that they are moving among the ships. If they are moving like 1, 2 to 10 meters above the water, it means they move along the ships and they need to be regulated a similar way. If they move higher than 150 meters, then they become airplanes. And yes, there are airplanes also today who can move in ground effect and vice versa. Ships, however, don't usually fly. Then there's 3 types that these two organizations have agreed on. Type A, that Airship is aiming for, is a vehicle that travels only in ground effect above the waters, and it will not be flying. Type B is such a thinking ground craft that occasionally comes higher than its ground effect allows and flies, but always flies under this 150-meter limit. And Type C are the ones that can do both. And that means also that Type C has to correspond to both regulations, shipping regulations as well as the regulations that are applied to airplanes. Who knows about aircrafts knows that to develop an aircraft is way more expensive to develop the ship because of the air pressure, because of the air tightness. In ships, we need just water tightness. So that makes it a bit easier to build them as Type A than any other type. Where can they be used? They are perfect for up to 1,000-kilometer routes, which means that they can be used anywhere between the islands in inland waterways and regions that are difficult to reach by traditional ships. Reason being that this vehicle moves on top of the water, which means that it can go over the shallow waters, which would be difficult for ships of significant size. Second, when we talk about the Baltic region, it would make the transport way faster, as speed 200 kilometers per hour would mean that the goods travel from Finland to Germany, for example, in few hours instead of few days. What does it look like? First view, it's still in design phase. We are still working on it with our partners. The main development of this vehicle is being done from technical side in University of Tampere. And this is one of the first designs that was thought of. There's many different ways how ground effect vehicles can be built. I'm not stopping on this, otherwise we can be here for quite many hours. Though it looks like a plane, it can float, hence the underside of it that reminds a bit of ship's hull. And the aerodynamic part you can see from the top side. It's all smoothed over, no abrupt ends. It has a tail, which is typical for the aircrafts, which enables us to control it a bit better. It has engines in a bit different position than usually aircrafts. Aircrafts have them under the wings or in the beginning of the wings. A ground effect vehicle has them always behind the wings. That's one of the main differences in designs when you look at the aircrafts or winging ground vehicles. Now, the first one is already able to fly. And first test runs were done last year in March on top of Lake Inari. It's not flying on its own yet. As you can see, it's being pulled. But it gives you an idea of how and which way this craft moves. As you can see, it barely lifts itself off from the snow and showcases very well that such crafts can move on top of any level surface. It doesn't have to be water. Water is just one media that can be used and one where we can develop it further. This project has been divided into 9 work packages. TalTech's responsibility is work package 2. But as you can see, there's work package for each subsystem that exists on this type of craft. There's design of the craft itself. There's power plant and power management, because the new vessel based on electrical engines will need new technologies for that as well. There's a separate 3 packages to make it fly. Perception avionics to make it fly autonomously. which means that aircraft in the end is supposed to travel on its own from one destination to another without any humans on board. Work package 5 is all about control avionics, controlling both flight as well as its mission. And work package 7 is detailed in mission control, meaning how to navigate, how to guide it from distance, how to make it completely independent. Work package 8 works on integrating them all together. In work package 2, we look at its environmental footprint, sustainability, and social impact, as well as on the possible business uses. Where could it be applied? Where could it be used to us? And work package 9 is typical dissemination outreach and road mapping, meaning having contacts with the outside world, making our work known, and having stakeholders interested in what we do. This all can be looked also from another point of view, like what we actually do. And this project is over 48 months, has timeline underneath. And it starts off with digital models, which means that we have a digital twin of this aircraft. It's already ready and we use it for testing and planning different operational modes. We have made some wind and water tunnel tests. We have A0 model for that. Currently, we are developing A0S model, which is already 1 meter by wingspan and can carry 3 loads of payload. So we can transport 3 kilograms of something with it. And the plan is to test that one in the end of the year. And by the end of the project, we plan to have a demonstration model ready, which is called AIRSHIP 1, which is up to 4 meters of wingspan and can carry up to 15 kilometers, moving already with a speed of up to 20 meters in second. The program itself is rather interesting because it combines technical, IT, avionics, robotics, and many other fields to put it together. So though we are aiming to showcase what AIRSHIP can do in the end of the project, the technology readiness level will not be above 4 on average. That's what we have promised to achieve with this project, because we cannot be 100% sure that situational awareness and self-awareness that we are also developing during this project will be ready enough for higher levels. As you can see, there will be 2 tests in the end. Avionics, perceptions, guiding, navigation, and will be tested on field, and situational and self-awareness together with power plant and power management will be tested in laboratory. That's why the TRL levels are different. So how big will it be? The first test version was done 120 in scale, 1.25 meters big. And that was the yellow one that you saw flying just on the slides before. The next version is 1/10 of commercial concept size, 2.5 meters. And that will be a flying prototype, which we will be testing in the end of the year. A1, the final technology demonstrator, spoken is about 5 meters, about 120 kilos in total of weight, and can carry about 20 kilograms of weight with it. Its cruise speed will be around 100 kilometers per hour, and takeoff speed before it can fly in ground effect will be between 65 and 70 kilometers. For takeoff, it will need only 4.5 kilowatts of power. So it's aimed to be rather efficient, and we hope to achieve that within the project timelines. The commercial concept that you can see is just for evaluating the business cases and its use and their environmental aspects. We are not intending within this project to build a commercial concept. It's just an idea that we have downscaled for testing purposes. So what will this thing have? It will have thrust lines, so it can move forward and down. It will have different possibility to use its tail in flight and for landing and for takeoff. It will have rather streamlined upper fuselage so that we have better aerodynamics. As you can see, the left side is the initial idea that we had, and now we are on version 6 in development. Results of the tests have all been taken into account, and as you can see, the winglets that were turned down before, so it was looking more like a trimaran, have now been changed to the airship winglets that are turned up. And as you can see, the underside has been developed further, so it's going now a bit deeper into the water than in the first trials, but it should also help it to be more efficient in water and help us to get it out of the water quicker. The idea is to have it fully electric and integrated at the same time with solar energy and fuel cells, which means that we will be having a zero-emission power system that can supply the power itself on a good day. So as you can see on the right-hand side on a photo, we plan to have fuel cells and solar panels on board so that it can produce its own power while moving. For energy storage, we plan to have batteries as well as supercapacitors, and if possible, also hydrogen storage, which we haven't promised out yet in the project documents, but as hydrogen is one of the future fuels, then it's best to be prepared if possible. And we will be using digital twin for testing all those different things. A big part of it, the project is to have it autonomous, meaning that no human on board. There's a lot of development going on situational awareness, led by our Luxembourg team, which tries to take advantage of all data that we can acquire today through different techniques, through different sensors, and make use of those to get situational awareness as far as possible. For that, we will be implementing many sensors all over this small craft that will be used for testing already in the autumn. It will have flight control computer, sensors, and servers. Shortly, it can be said that it's about 10 kilometers of cables fitted into 1.5 meter big vehicle. It will be interesting to see how they work. The pre-tests have already been done. Our partners have used a small vessel to test out how it sees the world and how it sees the sea, how it sees the object at the sea, how quickly it can give us feedback so that it can be developed further. As we are talking about the speeds that are significant, 200 kilometers an hour and above, then having this technology to work in a systematic and efficient way is one of the key to the success of it. And the first tests that have been done so far with different data sets and different technology have been rather promising. Especially when you look into these, how the masks show what has been seen by this technology today, then we are quite far in that field. Autonomous control means using different type of AI, and the plan is to use it for reinforcement learning, which means that we will use hybrid approach from model-based and model-free teaching of AI to understand what happens around it. Of course, it's physics-based and it's evolutionary. Both model-based and model-free approaches have their different pros and cons. And the team who's working on that is trying to do their best to take advantage of both models to avoid the problems of one in use of the other. Now, what have we been doing, and what is the team of TalTech doing in this? We are not developing avionics, as that's not our specialty. But our team of Professor Ulla-Piritta Tapaninen, Associate Professor Olli-Pekka Hilmola, Riina Osasson, and me, myself, we are working on the business sustainability and environmental impact side of it. which means that we have already done 2 deliverables that are in public domain, and you can go to AIRSHIP's homepage and read them. First year, our target was to do a sustainability assessment framework. And last year, we compiled business cases and did a business study, how to use and how to make money by using AIRSHIP. The next 2 years will be spent on social aspect study and environmental impact study, but about them a bit later. So the first year, we used several analyses. Most interesting of those, perhaps, is the PESTEL analysis, where we looked on the political, economical, social, technological, legal, and environmental aspects of this new craft, what it will be changing, what will be needing to be changed in laws, in our habits, in our surroundings. Where is it effective and where is it not effective? We also compiled a sustainability-based value capture system, which means that taking into account the 3 main systems that we have around us, economic, social, and environmental, we looked how we can make and bring value out of using AIRSHIP, meaning how we can make social value of it, how we can make life better for the people who use it, how can we make life better for the environment? Well, using electrical vehicle that has 0 emissions, that's clear for the environment. From the social side, as we all know, then when we compare electrical engine to traditional diesel engines of the ships, then electrical ones are usually quiet. So we at least reduce noise levels, if nothing else. And also pollution, cleaner air. And economic is what we did on the second year. So to build a business case, we asked where can we use the ship, who can use it, and what can be transported with it. And Riina Otsasson, together with Olli-Pekka Hilmola and Tulla Piritta Tapaneninen, and our partner from Canary Island, Beatrice Tovar, made a rather thorough analysis of different Canarian islands and transport routes between them, which would enable to transport goods faster. As you see, the route distances between those islands are not small, in average 600 kilometers, which means that transporting goods by ship takes time, and in case of emergencies, it's not that easy. So further from that, we looked into the stakeholders, like who would benefit most from using of this vehicle. And we looked at the business case from the operator's viewpoint, like if I have a company that's doing the transport, where can I utilize this the best? We looked at it from the regulator's point of view, producer's point of view, owners, employees, ports, and local communities. And this stakeholder view study is what is going to continue this year when we look at the social aspects of this vehicle. Of course, it's not on its own. It has competitors. We have aircrafts, we have land transport, we have water transport. So to find a business case, we needed to find the niche where AIRSHIP is the best. And its best size will come out in the mid-leg dominance, meaning transporting goods from ship to ship, not from consumer to consumer, because due to IMO and ECAO's agreement, wing and ground crafts are on water only. But its advantage comes from speed. It's faster, way faster than ships. Its advantage comes from landing on water, something that the aircrafts cannot do. It can fly and it can float, which means that it has its uses, especially in emergency evacuation places. But you cannot fly additional people in, but you can use automated ship to go and get somebody out or to deliver help. It has low operational costs. Our initial calculations showed that it can be used in the size that we are planning to do it, 4 to 7 tons of weight carried at one go. For any range close to 1,000 kilometers in one go. and its operational costs would be similar to the small boat that we use for fishing on the shore side. Its autonomous capabilities, of course, give it extensive use in emergency cases. For example, in cases if there's islands that are being overrun by hurricanes and they need quick release, or for example, in the cases where you have earthquakes and where sending an aircraft or even a helicopter would be impossible because they would need to fly there. But the airship's abilities to fly close to the water and to float give it extraordinary ability to fly as close as possible and then go further in the water. Part of this study was also a simulation model that's free for everybody to use. Operator use case simulation made with Insight Maker, which takes into account most of the costs that accrue around this vessel, personnel costs as well as development costs, as well as port costs and so on. And this simulation model gave us a nice possibility to see the cash flow and return on investment, which shows that roughly on the third year, such vessel would break even, provided it's used at least 5 days a week and doing flights at least 12 hours a day. As we are scientists, of course, we don't just do assumptions and do paperwork. We also publish our results in peer-reviewed journals. And out of this project, currently there's 4 published papers. That last one just got accepted, so I cannot share a DOI yet. But the others are available on AIRSHIP's website as well as on the papers where they have been published. This year, we do the social aspect study and our partners prepare for the trials of A0S. And next year, there will be by us an environmental impact study to see how it affects the world around us. And hopefully in the end of next year, the A1 trials will be taking place to showcase all that this project has been accomplishing. So this was shortly my presentation of what we've been doing for the past 2 years, what is the AIRSHIP project and how it moves around. So questions welcome.
Okay, thank you, Kristin. This was really, really fascinating. Let's see if we have any questions in the chat. Okay, I don't see any at the moment.
Can you hear me? I'm on my phone, but can you hear me?
Yes.
Yes, we can, Bente.
Well, yes, thank you. It was very, very good presentation, and I learned a lot. I have a question about this. Anybody has done any work about wave height effect, or can you fly over ice? Especially, anybody has done, is a wave height an important parameter, or is it any limit for wave height? And what happens above ice? Anybody knows?
If it's flat, it's perfect condition for this thing to fly. And as you saw, the Inari tests were done above the ice. So anywhere where you have flat place that can fly. And icy conditions for this is perfect. Also in that sense that if there's some breakage in the ice or there happens to be water in some places, it doesn't affect ground effect flight. Mm-hmm. When it comes to the wave height that it can take depends on the size of the vessel. The bigger the airship is, the higher it can fly, and that means the higher can be the waves. When we did the initial calculation for this project, we took the average wave height of Canary Islands, and we got that we need a craft that can fly in ground effect at least 4 meters from the average wave height. And that dictated the size of the craft of 25-meter wingspan.
Okay.
So if you go bigger, that means it can take bigger waves.
Yeah, okay.
If you go smaller, There is one craft actually done in Australia, which is for 2 persons. Very easy design, built of cardboard and plastic. And that can take wave height of 0.5 meter, which means rather calm seas.
Yeah,
But that's
okay.
also a small one. It's less than 6 meters in wingspan.
Okay,
They're
very
having
good.
calculations for big ones. Boeing has been planning Boeing Pelican in 2000s. And their wingspan was more than 100 meters, and they would have been able to take any wave that comes along. But the costs of that project were so big that they were disregarding it. It was over the limit that DARPA can handle.
Okay, very good. Thank you. Very impressive anyway. Very nice. Let's see what happens. Very nice project.
Okay, thank you. Actually, we have a comment here in the chat. Kristin, can you see the chat?
Yes, I can.
Alexander Majora has written some comments.
I think you could consider also heavy drones as a certain direct competitor when usage is similar. Yes, big drones can be competitor. Also, big helicopters can be competitor. Drones have a bit different way of moving around, and unless they move in ground effect, then airship will still have advantage in carrying the payload. However, drones do have advantage in last mile delivery because they can move high in the land, and airship is directed for the sea use only. To use it as aircraft, yes, it's possible. If you remember, then I will quickly go back to the slide. There is a possibility to make it such that it corresponds to both rules, flying rules as well as maritime rules. Just a second. This one. But that means that the initial costs of building it will be way higher, and we would need to have approval for flying it according to the ICAO flight rules, which means that as soon as we come to the ground and try to take off from airfield, it will need to be compliant to all the aviation rules. And that means that any component that's used on it needs to be certified separately. When the cost estimation was done, it's not tenfold, but about 100-fold what the cost level would rise to make it such with the plans that are there today, with the technology that's not existing yet that would need to improve. There's a project in America at the moment called Regent Sea Gliders, and they are having heavy battles between their Coast Guard and their FAA flight regulators. The flight regulators would like their project to be under their ruling, and the Coast Guard, a shipping regulator, is eager to keep it there. And they have said that they will stop the project if it goes under the aviation rules because it will not be feasible. It will not make sense. So for now, the answer to the second question is sorry, but no, not yet.
Thank you, Kristin. Do we have any more questions? If you have a question, please raise a hand. Okay, I don't see any questions in the chat or any hands in the Teams meeting. So I guess that's it. Thank you, Kristin, again for this presentation. It's really interesting, and I hope everything goes well with the project. So thank you, and I hope to see everybody on our next seminar in March. The info about it will be out soon.